Thank you very much for inviting me to this talk. Yes, I'm from ETIS lab in Cergy, and this year I'm also on sabbatical visiting an area in Paris. So actually the credit for this talk goes mostly to my former PhD student, Cécile Bouet, and my former colleague, Li Gongguan. And I will focus on covert communications. So what do we mean by covert communications? The idea is that in many applications, revealing metadata such as who is communicating, when and from where can leak sensitive information, even if the confidential message is not disclosed. And so the goal of covert communication is to conceal the very fact that communication is ongoing. This concept has appeared in different domains. For example, in steganography, you want to conceal information in a digital object, for example, in an image. You want to conceal the fact that there is a message. In telecommunications, we have spread spectrum techniques, for example, in military communications, where you spread your signal over a high frequency band and try to hide the message under the noise floor. And in this talk, I will consider the information theory point of view. So the problem with spread spectrum, for example, is that it is hard to provide, to prove that theoretically that you can conceal the message. So here we focus on the information theory point of view, where we want to ensure that an eavesdropper has a low probability to detect the communication. So the model I will consider is a simplified model in which I will assume that so the legitimate receiver Bob and the eavesdropper Eve see exactly the same output signal, and so Bob needs to have an advantage compared to the eavesdropper, otherwise it is not possible to communicate covertly. And so we will assume that Bob and Alice share a secret key. So of course we want Bob to reliably decode the message, and then the covertness condition is that the eavesdropper should not be able to tell whether communication is ongoing or not. So basically, the eavesdropper performs a hypothesis test and tries to say whether there is or not communication. So as you can see, we have a link with the hypothesis testing. So the eavesdropper receives a sample from the output distribution and must decide whether this sample was produced by the distribution without communication or by the average distribution of the covered code. So here the code is known. The only thing that is not known is by Eve is the value of the secret key. So it is known in the theory of hypothesis testing that the sum of the probability of false alarm and of misdetection, so of supposing that H0 is true when it's false or vice versa, is lower bounded by 1 minus the variational distance between these two distributions. And so one criterion could be to ask for this variational distance to be small to guarantee that the sum of probability of false alarm and misdetection is large. And some papers indeed consider this criterion. In this work, we consider instead the KL divergence as a proxy for the variational distance. So it's a bit stricter criterion, but it is easier to work with. It's stricter because we know that if the divergence is small, then the variational distance is also small by Pinsker inequality. Okay, so first some state of the art. So this area of covert communication, the whole framework in information theory was first proposed by Professor Bash, who is in the audience today, and also in another paper by Che, Bakshi, and Jaggi, who showed that the maximum amount of information that you can transmit reliably and covertly if you have n channel uses, scales like square root of n. So in this sense, the channel capacity of this channel in the classical sense is equal to 0. And then Wang, Warnell, and Zhang and Bloch characterize the scaling constant in front of this square root of n for discrete memoryless channels and AWGN channels. So yes, in this talk, we are interested in this scaling constant that I will define as follow. So let's consider the highest possible cardinality of a code that is at the same time reliable and covert. And then I divide by square root of n delta, and I take the limit when n goes to infinity and when epsilon goes to 0. So you see there is quite an asymmetry in the two criteria. I asked that the KL divergence should be bounded by delta, but I asked for the error probability to go to 0. Some other papers consider a notion of covert capacity, which is maybe catchy. Okay, so in this talk, I'm interested in continuous channels that are additive. So here, Py0, so the output when there is no communication is simply the distribution of the noise that I will call PZN. And the simplest example is, of course, the Gaussian channel, so the IID Gaussian channel, where Zi is independent Gaussian. And in this case, you can show that L is equal to 1, independently of the noise variance. So in this work, we consider 3 generalization of this of the AWGN setting. The first is the Gaussian channel with memory. And then we look at general memoryless channels that they're additive noise, but not necessarily Gaussian. And finally, want to see what happens when we allow a non-vanishing average error epsilon. So I will actually spend most of the time on the second case. Okay, so the Gaussian channel with memory actually turns out to be quite easy to deal with, at least in this formulation. So we suppose that for each n, the noise is a Gaussian process with some mean mu n and the covariance matrix sigma n. Then you can show that once again, L is equal to 1, irrespectively of mu n and sigma n. And actually, the reason the proof is quite simple. Basically, we know that there is an affine transformation that sends the noise Zn into an IID noise, and then for any code for the Gaussian channel with memory, we can easily define a code for the IID model. And you can show that these two codes have the same error probability and the same KL divergence. So in this sense, the result is almost trivial. Okay, so let me move on to the memoryless additive case. Why do we care about non-Gaussian channels? Well, because experimentally, in many scenarios, noise is not Gaussian, and in particular, if we have networks with interference, it can be heavy-tailed. And intuitively, one can think if I have heavier tails, it is easier to hide the fact that there is communication. So maybe this can increase the scaling constant. So we will show that we have a general upper bound for L, simple expression that depends on the noise PDF. Under some additional conditions, we also have an achievability. And we also want to give bounds on the size of the key that is required. Okay, so our theorem is valid under some technical condition of integrability of PZ, of the noise distribution. And we show that L is upper bounded by square root of 2, square root of variance of log PZ of Z. In fact, after we published the paper, Olivier Rioul pointed out that this variance of log PZ has a name. It is called the var entropy of the noise. It is the variance of the information content. So you remember that the entropy is the expectation of the information content, and this is its variance. And in fact, it's quite intriguing that this appears. I will quickly give an idea of the proof. Basically, we are interested in the maximum amount of communication that can be sent under a divergence constraint. So first we characterize the distribution that maximizes the entropy for a given divergence to PZ. So it turns out that this will have the form PZ to some exponent. And then we add a normalization constant to have a density. This is called apparently an escort variable in probability theory. And then we choose the exponent gamma n in such a way that we have the divergence from PZ tilde to PZ is delta over n. And we can, by the Taylor series, we can show that this gamma is of the order of 1 over square root of n. And then we can singularize our problem by taking the average output over all channel uses and also average over the keys and the messages. And so by the previous lemma, we have a bound for the entropy of this average output. And then to prove the cardinality bound, we know that we can bound the log of m by the mutual information of this average input and output by Fanus inequality. And then we use the fact that the channel is additive. So we can decompose it into h of z tilde minus h of z. And then it's just a computation. Okay, so when is this upper bound achievable? To prove it, we need some additional conditions. Some are technical. We need PZ to be bounded and the PZ log PZ to be uniformly continuous. And then we assume that there is an input x such that the distribution of x plus z is the optimal output z tilde. So if we have this, then we have equality. So L is exactly equal to this quantity. How much time do I have? Okay. Okay, so just to give an idea of the achievability proof, so we assume that we have such an optimal input, and then we generate an IID codebook using this input. And note that the input pxn depends on n, so we cannot use a classical random coding argument because of this fact that the input depends on n. So we consider the same gamma n as before, and to show covertness, we decompose. We want to show that there exists at least a covert code, so that the average overall codes is covered. We can decompose the divergence into 2 parts. So for the second part, if we choose gamma n as before, we have a small divergence. And for the first part, if we assume that the key is sufficiently long, then we have a convergence of the output of the code to PZN times n. And I will come back to this question, what sufficiently long key means in a moment. Okay, so just an idea of the proof of achievability. Suppose we have this assumption one is verified, then since we have convergence of the KL divergence, we can also show that we have a weak convergence of PZ tilde to PZ. And then using the characteristic functions, we can also show that the input xn converges weakly to Dirac delta, which also tells you that this achievability scheme is not very practical. Okay, as I said, we cannot use a standard random coding because Pxn depends on X, but we can use an information spectrum approach to say that there exists a sequence of codes such that log m is lower bounded by the information density. And then we show that the information density converges in probability to the mutual information. So for this, we use the fact that Pxn tends weakly to the Dirac delta. And then since we know that Pz tilde maximizes the entropy, we can prove the achievability as before. Oh, sorry. So this concludes the achievability proof. Just I want to show some examples where we can apply our theorem. The first is the exponential noise channel with some parameter lambda. Why is the hypothesis verified that there exists an input with the output Pz tilde? This was actually shown by Verdu that if you take as input a mixture of an exponential and Dirac, it will have exponential distributed output. And so finally, we find that L is equal to square root of 2 independently of lambda, like similarly to what happened for the Gaussian case. And the second example that I want to show is the family of generalized Gaussian noise distributions. So this family includes the Gaussian when p equal 2 and the Laplace distribution when p equal 1. For a smaller, where p is smaller than 1, we have a heavy-tailed noise. So we have a general upper bound that L is smaller or equal to of square root of 2 over p. And then we have equality at least for p in 0, 1 and p equal 2. So we see that the intuition is confirmed in the sense that the smaller the p, the heavier the tail, and the better we can hide. We can conceal the communication because extremal events become more likely, and so the covert capacity increases. Okay, so up to now, I have assumed that Alice and Bob share an arbitrarily long key. But now we would like to check that this key is not too large, especially compared to the message. So in general, unfortunately, we are only able to show that the size of the key is at most of the order of n, which is a bit disappointing because the message is of the order of square root of n. But for the Gaussian and exponential, actually small o of square root of n is enough. For the Gaussian, this was already known. I think it was proven by Mathieu Bloch. And so to show to have the bound on the key size, we use a Chandler resolvability bound by Hayashi and Matsumoto. I don't think I have time to go into details. Okay, so what are the takeaways for this memoryless general case? So it is quite surprising that we were able to characterize L for quite a general class of channels, including some cases where we don't even know the Shannon capacity. This is due to the fact that somehow we can, the covariance condition translates to an output constraint that is fitted to the noise distribution. And just a remark on the achievability. So the input distribution in our achievability might not be unique. For example, for the Gaussian case, you can use Gaussian inputs with power 1 over square root of n. But you can also use BPSK, which is much more practical, and both achieve the optimal scaling. So what remains open is to characterize L for general additive channels with memory, hopefully maybe stationary ergodic, or at least a Markov. Okay, and then the third generalization I wanted to talk about is the asymptotics of L for when we allow positive error probability epsilon. So it is known for DMC that there is a difference if you consider maximal error probability or average error probability. So the max over keys and messages, or the average over keys and messages. So in the first case, the strong converse holds and the L epsilon is independent of epsilon. But in the case of average error, it does not hold. So the L epsilon will depend on epsilon. The same is true for the AWGN channel. And so we consider the second scenario of average error and show some upper and lower bounds for L epsilon. Unfortunately, we still haven't managed to characterize it. So why don't we have the strong converse? The idea is that the covertness constraint implies an average power constraint. And so we are back to we are in a setting where we have average power and average error for AWGN. So even in the classical case without covert constraint, in the Polyansky's thesis, it was shown that the strong converse does not hold in this case. So that's why we have this situation. So we define L epsilon as before, but so we fix epsilon. This time we don't take the limit when epsilon goes to 0. And what we are able to show is that L epsilon is comprised between 1 over square root of 1 minus epsilon and 1 over 1 minus epsilon. So I don't know which one is the correct one, or maybe none of the two. Probably I would say this if I had to make a bet. So the takeaway of this result is that if you allow a small error probability epsilon, a positive error epsilon, then you can transmit additional covert information. And yes, so the finding L epsilon is still an open problem. One could also consider other covertness metrics, such as the total variation. And in the case of maximal error, okay, I wrote this as an open problem, but I think there are some recent papers maybe that study the second order asymptotic. Okay, so I think I'm done. Thank you very much for listening.
Yes, thank you very much for the talk. Are there any questions? Yes.
Thank you for the nice talk. First, I have a comment. I've already mentioned this to Ligon, at least on one occasion, who I think you worked with on this initially. I think he's on your paper or papers on this. But I understand that the metric L arises because you have adversary and legitimate receiver look at the same channel. If you look at the very, very beginning of your talk.
Yes, indeed.
So there is a practically meaningful interpretation of the constant in front of the square root of n as a signal to noise ratio. If you actually use two different channels It's actually a ratio of signal to noise ratios.
Yes, for AWN, I think it is. Yes, it's the ratio of sigma Eve to sigma Bob. Sorry, or is it the opposite? Sorry, sigma Bob over sigma Eve.
Right.
But actually, for the non-Gaussian case, I don't know. In fact, we really need this hypothesis in our work. I don't think we can generalize to. So it's not only for convenience, but the problem would be a lot harder if you have two different channels.
Well, that was my question. So for a Gaussian case, it's fairly apparent that interpretation is right there, and it's nice. But for your case, where you have two different, where you have a channel which is different than Gaussian, I think it would be meaningful and interesting to consider that. Because
yes, I think so. Cecile tried the PhD student, but it's not at all trivial how to generalize this. So I think she had some partial results for the exponential, where both channels are exponential, but for different lambdas.
Mm-hmm.
But in general, if you have two different types of channel, it's too challenging.
Just because the problem is hard does not make it interesting.
Yeah, it's interesting, but we were not able to solve it.
It's fine. It's fine. No, I understand. And I think it also would make the second order result you have a lot more meaningful as well for practitioners. Mm-hmm. But overall, this is great work. So thank you.
Another question.
I had one question. You mentioned that you're able to get single letter characterizations in scenarios where the plain vanilla channel doesn't have single letter characterization. And can you elaborate more on that, please?
Sorry, can you repeat?
You mentioned there are circumstances where the covertness condition will impose a single letter characterization.
Okay, I did not say this, and I'm not sure. I don't know. It's a good question. But basically, I think in some cases it imposes an output cost constraint, which, for example, yes, for the Gaussian, it's average power constraint. For the exponential, it's an average. No, it's a peak. Sorry, it's a L1 constraint. And so I think it would be interesting to more generally study this output cost that comes from the covertness. So I don't know about single letterization.
I thought maybe I heard you say that the output constraint.
No, what is surprising is that we can get this L for cases where we don't even know the capacity. But
that's
yes.
what I was.
But maybe that's due to the fact that the two channels are the same, and so they are aligned in some sense.
Can you also please elaborate on one point you mentioned about this Polyansky's thesis, where you said that the strong converse is not available for? Can you please elaborate what?
Yes,
I'm just curious about that result.
I think in the 2009 paper, I don't know if this case is treated, but it's certainly in the PhD thesis. Yes, if you have average error probability and the average power, then yes, there is no strong
plain vanilla Gaussian channel.
Yes.
There is no strong converse.
Yes. So I think this was not this case was not treated in the famous paper by 2009. Okay. No, 2009.
Thank you.
It is only in the PhD thesis.
Okay, thank you again.